Hey, what's up, guys? I'm back with another system design interview. Recently, I've been sort of jumping around a couple different topics. I've been switching jobs, but I wanted to get back to the reason why you're on my channel in the first place, my system design interview videos. And I'm gonna go over one that somebody mentioned in the comments that I thought was a cool problem, which is design a video streaming service kind of like Skype and Zoom or FaceTime. And this is something that I actually was thinking about recently since um, there's a couple ways that you can do this. You could have a middleman server that relays the packets to the respective devices, or you can try to establish a direct link between service A and service B. So the reason why you might want to have a middleman server is because it's much easier to get that information across on the internet, because the internet is broken up into three different layers, or multiple different layers. Not, I wouldn't say three. You have the DNS server, which the client attempts to connect to, and the DNS server basically routes it to another server, your final destination. So the way the internet works is you might, for example, want to look up like google.com. And by looking up google.com, you're not entirely sure what google.com's IP address is, because that is the actual that's the actual address of the server on the World Wide Web. In addition to that, there are other various issues, like for example, a server could be hidden behind some sort of router. So the router actually owns the IP address, and then the final computer, which is the destination, is hidden behind this router. So the destination doesn't actually have its own IP address. The destination has a local IP address, while the router or the IP has the publicly available IP address. So then this gives another problem of like subnets and port and routing, which is a whole another mess to deal with. So it would be actually very hard to establish a direct link to the destination. So let's just assume that both of these computers just interact with a middleman server that they're able to talk to. So now that we like sort of talked about that, I'll explain why it's important in just a second. If you haven't taken the time, please like and subscribe. That gives me motivation and helps me sort of know I'm doing a good job explaining these system design questions. And if you have any ideas for new videos, be sure to drop it in the comments. I do look at those, even though I don't respond all the time. I have a full-time job, so I try to respond when I can. But if you have any good ideas or you want to give feedback, just drop it in the comments. I always read them. So even if I don't respond, I'm sorry. I have a job and I have a life, so I want to. I do that after work, and I do come back to the videos, and I don't forget about you guys. Just like drop it if it's something that I should respond to. I'll respond. I'll like it. So yeah. Let's go over requirements. So this should be the first step before even designing an interview and a system design question before even approaching it, because this is sort of what the big difference between somebody who's inexperienced and somebody who's experienced is the requirements can completely change the nature of the question. So let's go ahead and define the requirements as need to be able to create a video call between client and destination and receiver. Let's call it receiver, and needs to be able to handle multiple concurrent video calls. And I think another really important thing is that this service is available globally. So US can call China, which is on the other side of the world, and vice versa. So there's some nuances that these requirements add to the problem. So I'd like to hone in. I'll go over each one individually. So you need to be able to create a video call before a client and a receiver. That's very straightforward. That's a basic video calling application. So the second one is need to handle multiple concurrent video calls. So that means that this program can now scale. So then that leads to another question of how many concurrent users at the same time, which is sort of basically asking how many video calls are going on at the same time. And for all intents and purposes, let's say like at maximum there's 1 million video calls. And then the last bullet point, that this service is available globally, US to China and vice versa. So what does this tell us? That means that we need to keep a certain minimum latency, because if a video has any lag and suddenly becomes hard to watch for the people in it. So I think that the actual latency that it starts becoming a problem is around 100 milliseconds delay, and this causes, if it's greater than this, then it causes awkwardness. So let's do causes bad user experience, and this is something that you can do to really show your knowledge of how much you know about computers, and understand that there is a round trip time necessary for distance. So the internet is basically a series of wires that are connected via light. So data travels through the internet at about 0.3 times the speed of light. So the entire distance around the world, I forgot the exact number, but let's just assume that it's miles, 12K miles. Actually, let's figure out circumference of the Earth. Yeah, so I was actually pretty close. And then, so let's take the speed of light. So the speed of light is about 300 million meters per second. So 1,200 miles to meters. This is about meters. So now we have these two equations, or two numbers. We can sort of find how long it'll take to get across the world in across the world using how long it will take to get our packet of data across the world. So let's do this calculation. It takes about 15 milliseconds to, did I do that right? So this is seconds. Yeah, it takes about 64 milliseconds one way to get from US to the other side of the world. Therefore, by having to do a round trip, that's 2 times. And why is this important? I'll let you know. I'll show you in just a second. So a round trip time around the world through the internet is about 128 milliseconds. So there's two types of internet protocols. There's UDP and TCP, and theoretically, TCP is built on UDP. So what's the difference between UDP? UDP is unordered, and TCP is ordered and guaranteed. So UDP is unreliable, and it's just data packets being sent from server A to server B without any guarantee that they've arrived. However, for TCP to work, there's a back and forth transaction. So server A in UDP, server A sends packet A, B, C, D, E to server B, and server B can receive A, C, D, E. So it lost packet B, and maybe it gets B later on. So that it receives it out of order. This is fine for some applications, because if packets are real time, meaning late packets aren't relevant anymore, that means that we can use UDP and then discard late packets. In comparison, TCP is guaranteed and ordered, but in order for the guarantee to happen, I believe it has to send an acknowledge. So this is what happens when we send this over TCP. And I'm a little rusty. I haven't worked with networks in such a long time. So it gets A and then acts A, then gets B and then acts B, and then C and then act C. So the act just means acknowledge, and it sends the packet back to server B, and the server B receives an acknowledge before sending the next packet. So this is where it gets really important, because for server A to send packet A and then send packet B, it needs to wait for packet A to come back, which comes back to 128 milliseconds, which now breaches our 100 millisecond SLA, which is service level agreement between these two servers. So that means we basically ruled out that we can't use UDP for this, or we can't use TCP for this video calling use case. So that means we need to build a service built on a custom UDP protocol, because we don't want to receive packet A, C, D, E, B, and then when we receive packet B, suddenly we get a glitch and the server messes up. So we want to create some sort of UDP protocol that discards late packets. Cool. So this is a protocol that we're going to use. Now let's get into the actual laying out of what is going to happen. So we know we need a server, which is sort of like the routing server. And I think we want WebSockets because I don't, REST would take way too long. We would need, REST is based on TCP. We can create a TCP keep alive connection, but I actually think using WebSockets as our technology makes more sense. And WebSockets basically keeps a live connection to the server so you can send new packets without having to create a new connection. Pause real quick. Okay, I'm back. So now we have the routing server. Let's create our caller. Let's call the client the caller now. And the caller, when we initiate a call, let's call this initiate video call, sends a request to the routing server, and it passes a string, which is the receiver ID. So the receiver ID could be like a username or something of the receiver. The server will route it to a receiver. The server will keep a log of every receiver ID followed by the IP address or the socket connection of that receiver, and it can keep this in some sort of cache. And then it will send a call to receiver, which is pending call string receiver ID. When the receiver gets a call, it can choose to accept the call. And once it accepts the call, the server will now create an active room where the caller ID is mapped to the receiver ID. And then we can also create a reverse mapping of this, since we're going to be receiving packets from both sides. So now, once we have this call established, the caller will always be connected to the server, and the server is now connected to the receiver. So let's clean this up a little bit. When we actually want to send data, remember we want to use a UDP protocol because we don't want to wait on packets to be received before sending the next one, we just want to relay packets. So we can create a relay packet call, and then we can send packets as a byte array. And then once we get to the routing server with these packets, we can do a lookup of the caller ID, and we can pass the caller ID here, or we can pass it in the header. We can look up who the receiver is, and then the server will just send those packets to the receiver, which could be another function called deliver packets caller ID, or packets. And then this can also be reversed on the receiver side, which is calling the same WebSockets function. And then this can also deliver the packets on the other side. Cool. A way to simplify this is we can actually, instead of passing the caller ID, we can just do a room ID. And that way, that won't actually work. I mean, that'll make it a little bit more complicated. But we could just add some code to deliver it to the person who isn't calling relay packets. But that might actually be more trouble than it's worth. Let's just keep it simple, just for like some fault tolerance, or just to take out like potential error. So this is great, but this won't scale. This can handle maybe like one video call at a time. So we need to scale this horizontally, meaning that we need to have more routing servers, and we need a load balancer in order to like send the calls to the right routing server. So let's clean this up a little bit, because it's going to be messy drawing on that one. So then let's just horizontally scale this design. So let's just create multiple routing servers. Let's move receiver to this side so we have some more room to play with. So now, and then let's add a load balancer. So the load balancer basically will get the status of every one of these routing servers, see which one is under capacity, and then route a request to the right routing server. And each routing server will be agnostic. It will literally just handle the packets to like find the actual destination and then return it. And then we can add a data store over here, which is like a quick lookup. We're literally creating a hash table, so Redis is a perfect use case of this. And all of these are connected to a single Redis cluster because Redis is single core. So yeah, this is sort of how you would horizontally scale the system. Very simple. We can add more frills if we wanted to, like storing like room IDs and stuff later on, or like storing the actual video calls. But this is how you would approach a real-time video streaming app. And if you haven't done so already, make sure you hit that like button and hit subscribe, because it really helps me like sort of get motivation and like just sort of like keep going at this. I know it's I know I know that I really appreciate you like stumbling on my video and all the love that you've given me. I hope to keep you guys like good with like new content, and like keep like creating these videos. That those likes and subscribes like really help me. And if you really enjoy my content, if you don't enjoy my content, there's no hard feelings. You don't have to subscribe, but I really appreciate it if you do. Yeah, this is sort of the meat and bones of creating this like video streaming service. Um, the calculations in the front are really where it the hard part of this design is picking the right technologies and making sure that you don't get tripped up later on. This question does require some actual knowledge of how networking works. So this could be asked to understand like how much the candidate actually knows about computer systems. I don't. Most people, I don't, unless you like are like a genius and study computers like all the time, probably won't know about this internet latency, or like why the internet latency exists. So yeah, if you think you like this video, like and subscribe, and stay tuned for more system design content. Peace, guys.